Figure 2 shows a sketch of y equals ln x all squared. Note this is different from ln x squared, where we're only squaring the x. Here we're finding ln x and then squaring it. The finite region R, shown shaded in figure 2, is bounded by x equals 2, x equals 4, and the curve in the x-axis. And then we're given a table showing corresponding values of x and y with the value of y given to 4 decimal places. We're asked to use the trapezium rule with all the values of y in the table to obtain an estimate for the area of R, giving our answers to 3 significant figures. So we are splitting this shape, which, by the way, also already looks quite like a trapezium. So I'm splitting it into half, where that 3 is, and then half again. So I'm going to get 4 trapezia. They're going to be equally spaced. Okay, my sketch doesn't quite highlight that, but that is going to be the case. And even if you didn't draw those lines on, as soon as you've got 5 values, it means there's going to be 4 trapezia. So here's the trapezium rule. We can refer to the formula book for that. So for us, I've got the integral from 2 to 4 of ln x squared. And I'm just going to write it down with the 4 trapezia. So it'll be half h, then y0 plus y4 plus 2 lots of y1 plus y2 plus y3. Just a reminder, this comes from finding each of the trapezia separately. So this one, in which we use x0 once, and we get the y0, and then this one we use x1, but we also use x1 for the second trapezia. So that's why you end up with 2 lots of y1, y2, y3, but only 1 lot of y1 and y0 and y4 because they're on the end. I'm not going to go into any more detail on the formula. We're given it, but do make sure you understand it. Okay, so for us, we've got that h is going to be 0.5. That's what it's going up in. A is going to be 2. B is going to be 4. N is then going to be 4 as well. And this all tallies together. If you did 4 minus 2 over 4, you would get 0.5. Okay, so therefore it's going to be approximately a half times 0.5, and then we substitute in 0.4805, first one, and then the last one, 1.9218, plus 2 lots of the rest. Okay, and then just carefully put that into your calculator. Okay, hopefully you're trying this along with me. And what do we get? Right, we close the bracket there, and then again, 2.408025, which to 3 significant figures is 2.41. Now, one other thing to do in this question, I strongly advise it, is to actually just use the numerical function on your calculator to figure this one out. It's a way of checking your answer and also seeing how good the trapezium rule is. We're expecting it to be close. In fact, I'm expecting it to be very close here because of how straight that line looks. And you can see we get 2.41 to 3 significant figures as well. So we're really confident with that answer. Now on to algebraic integration to find the exact value, which at the end we can check if it is 2.41 by putting it into our calculator. Now I've done a lot of integrals in my time, but I don't actually remember ever doing the integral of ln x all squared. So this might be new to you. I couldn't remember having done it myself. So how are we going to do it? It's not like a standard integral or anything. Ln x is always a bit awkward. So integrate ln x, we integrate by parts. So that is a possibility. Could we do a substitution? Is that another possibility? Turns out you could do either. The substitution route is a little bit, well, it's a fair bit more awkward. So let's go with by parts. But then the question is, do we write ln x times ln x and let 1 equal u and 1 equal v dash? Or do we go with 1 times ln x squared? And the answer is to do this one, because if you do ln x times ln x, you're going to have to integrate ln x, which you're going to have to do by parts as well, which we can avoid if we use this approach. So ln x all squared is going to be my u, and then 1 is going to be my v dash. So u dash then becomes, I'm going to be using the chain rule, 2 ln x. When I differentiate the outside, it's something squared, so then it's 2 times that something. And then I times by the derivative of the inside, which is 1 over x. Whilst v is going to be the integral of 1, it's x. Okay, so then it's going to be uv minus the integral of u dash v. Don't forget the limits though. So uv becomes x ln x all squared, evaluated between 4 and 2, minus the integral between 2 and 4 u dash, that's 2 ln x times 1 over x, times v, which is the x. Okay, these are going to cancel, and we are going to actually have to integrate by parts again to deal with the ln x. So I'll just do that down here, I think. Forget the limits and everything. Let's write it as 1 ln x. This is the approach you take. So now ln x is going to be u, 1 is going to be v dash in a similar sort of way. U dash is 1 over x, v is x. So uv then becomes x ln x, and it's the integral of u dash v, which is actually 1 over x times x, so 1. And we get x ln x minus x plus c, but I don't need to worry about that here because we're dealing with a definite integral. So before I put any limits in, let's just tidy it up. So I'm going to have 2 lots, because I ignored the 2 when I did this integral, x ln x minus x, and that is evaluated between 2 and 4. Brilliant. Okay, let's sub in. So 4 times ln 4 all squared minus 2 times ln 2 all squared minus 2 times 4 ln 4 minus 4 minus 2 ln 2 minus 2, but that's going to become a plus 2 when I get rid of the brackets. I'm just going to do that straight away. Okay, let's not forget we're being asked to basically write it all in terms of ln 2. This is, this is quite commonly asked when you deal with a definite integral, to leave the answer exact, and it tests us on our logarithms and so on. So I can write ln 4 as 2 ln 2, because it's 2 squared, ln 2 squared, bring the 2 down. So then if I square that, I'm going to get 4 ln 2 all squared. So I'm going to get 16 ln 2 all squared. Then minus 2 ln 2 all squared. So I can simplify that in a minute. And over here, I've got 2, I'll keep that in a bracket for the moment. 4 ln 2 minus, 4 ln 4. Well, that's going to become 8 ln 2. So then I'll get 6 ln 2, and then it's minus 4 plus 2, I'm going to get a minus 2 there. That's going to give me 14 ln 2 all squared minus 12 ln 2 plus 4. Okay, and that is the answer, the exact answer to the integral of ln x all squared. Like I said, let's just check it, because we know it should be 2.41 to 3 significant figures. It's so easy to make a mistake here. It's got to be said like when you're just going between these things. So 14 ln 2 all squared minus 12 ln 2 plus 4, and we get the 2.41 again. Okay, one more method. Even if you can do an integral, it's quite often insightful to try a different method. It kind of builds your understanding of when something's going to work and when not, and sometimes when both will work. So I'm going to do a substitution here. It kind of only makes sense to let u equal ln x. Then du by dx will equal 1 over x. So dx by du will be x. I'm going to also change the limits here. So when x is equal to 2, u is equal to ln 2, and x is 4, u is ln 4. So let me just change it to u equals ln 4, u equals ln 2 to remind myself I've changed those limits. Ln x is going to become u squared, and then I'm going to replace it by dx by du, which becomes x du. You might be somebody who simply makes dx the subject, in which case you'd replace dx by x du, same thing. Okay, now I can't integrate this because I've got an x in there at the moment. So I need to get it back in terms of u. And if u is ln x, then x is actually e to the u. And now I've got an integral that you may be familiar with, okay? This is your classic integration by parts at this point, but I'm going to have to integrate by parts twice. So you can see this substitution method is arguably not the best because I've had to integrate by substitution, and then I've still got to integrate by parts twice, whereas in the other method, I just had to integrate by parts twice. It's slightly more standard though. That's the only good thing about it. So I'm gonna just momentarily change it to be into, I did a u substitution because that's what we normally do, but then when we integrate by parts, we normally let one of them equal u. It's a little bit confusing, so I can just change it to t, why not? Then that is going to be my u, that is going to be my v dash. U dash is 2t, and v is e to the t. So u times v, t squared e to the t evaluated between ln 4, ln 2, minus integral of 2 t e to the t. Okay, again, I'm just going to work that one out over here. I think, again, I'll ignore the 2 for the moment. So I've got u, v dash, uv becomes t e to the t, u dash v becomes the integral of e to the t. Okay. I'll just hold off on putting the limits in again. So now I'm going to get minus 2 lots of t e to the t minus e to the t. Okay, let's sub in. So I'm going to get ln 4 all squared, and then e to the ln 4. Now e to the power of ln cancels out. So I'm just going to get 4. And then it's going to be minus ln 2. You can kind of see some of the similarities already appearing now. Times e to the ln 2, that's going to be minus 2 ln 2 all squared. Then minus 2 lots of e to the ln 4 is 4 again, so 4 ln 4 minus 4 minus 2 ln 2 minus 2, but that becomes plus 2 again because there was a bracket around it when I had the minus. So I can just ignore it, but you put it in if you want, if it helps. That's what we're going to get eventually. Okay, I kind of feel like this is almost carbon copy, but let's just go for it again. So ln 4 is going to be 2 ln 2. So when I square it, I'll get 4 ln 2 all squared, so I'll get 16 ln 2 all squared. Similar thing. Okay, that stays as it is. Minus 2 lots, right? That becomes a 2 here and an 8 here. So again, I'm going to get 6 ln 2 minus 2, which gives us 14 ln 2 squared minus 12 ln 2 plus 4. Okay, so I advise you do the first method. It's a little bit quicker for sure, but this method would work as well if you did go down the substitution work. Anyway, thanks for watching to this point. Good effort on this question, and yeah, keep practicing your integrals. This is not an easy integral. They don't tell you the substitution. They don't tell you to integrate by parts. You have to figure out, actually, you can do either, the approach, but yeah, well done.